In this lesson, we're going to take another look at organic nomenclature, this time learning how to name alkenes and alkynes. Remember that an alkene is a compound that has a carbon-carbon double bond, and an alkene is what's considered a suffix-modifying functional group. Unlike things like alkyl substituents, which were placed at the beginning of a name as a prefix, like methyl, alkenes are actually incorporated into the name by modifying the end of the name. In this case, the parent chain, alkane, so ethane, propane, the ending ane is replaced with ene to designate that it's an alkene. So the simplest alkene would be a two-carbon alkene, derived from ethane, the simplest two-carbon alkane. So we change the ending to ene, and we have ethene. When determining the parent chain, when we have a suffix modifying group in the molecule, we actually have to modify the old rule that says look for the longest carbon chain. When you have a suffix modifying group, the parent chain will be the longest carbon chain that contains the functionalized carbons. And alkenes are actually what I call shared functional groups. Unlike other functional groups like alcohols and amines, where the functional group is attached directly to one carbon, an alkene actually shares the double bond, the functional group, across two carbons. And that means that for alkenes, both carbons of the double bond must be incorporated into the parent chain. So the parent chain will be the longest carbon chain that actually has both of those alkene carbons. So if you look at this example here, we actually have an 8-carbon chain running across horizontally. But that 8-carbon chain does not incorporate both carbons of the alkene. The longest carbon chain that actually has both of those alkene carbons is a 7-carbon chain, here in blue. So you can see that this is actually going to be a heptene molecule with a propyl substituent attached. So when naming any compound, we start by finding the parent chain, and then we number the carbons of that parent chain. Now, suffix modifying functional groups have a numbering priority over prefix groups like alkyl groups. So what we do when numbering the parent chain for an alkene or any other suffix modifying group is we start on the end of the carbon chain that is closer to the suffix group itself. So in this example, the parent chain is the 7-carbon chain going left to right, and if we were to number that carbon chain starting on the right, that would place the methyl substituent on the 2-carbon, but it would place the alkene on the 4-carbon. Starting from the left would place the methyl group on 6, but now the alkene on 3. And the alkene, being a suffix modifying group, has a numbering priority over that methyl group, which is a prefix modifying group. So we have to give the alkene the lower number, again starting from an end of the chain. And that means this is numbered left to right. So now we can see that the alkene is actually shared between carbons 3 and 4. To describe where the actual alkene is on the parent chain, we add a locant value for just the lowest number of the alkene. So in this case, the alkene is shared between 3 and 4. We simply add the locant value of 3. It's implied that the next carbon will be the next carbon of the double bond. The locant value for that suffix group is placed directly in front of the parent name. So in this case, that means that we have a 3-heptene, a 7-carbon chain that is an alkene, and the alkene starts on carbon 3. From there, everything else is kind of the same as it was before with alkanes. We simply place any substituents in front of the parent name, listing them alphabetically, each with their locant. So in this case, we have a methyl group on 6, so this becomes 6-methyl 3-heptene. In our other example here, we can see again that that parent chain that we found before is the 7-carbon chain starting on the top right, because we need to number it such that the alkene gets the lowest number possible, but again starting from an end. So that places the alkene starting on 2, so this is going to be a 2-heptene, and then we have a propyl substituent on carbon 3. So this is just 3-propyl 2-heptene. Remember that alkenes can have stereochemistry, geometric isomerism. Remember that when assigning stereochemistry to alkenes, we use either the cis-trans or the EZ system. And the stereochemistry, if there, should really be incorporated into the name of the alkene. Remember that when you have a di-substituted alkene, using the cis-trans notation is perfectly fine. So in this case, we have cis-2-butene, where we have the two methyl groups on the same side, the lower side of the alkene. And here we have trans-2-butene. We also have the option of using the EZ notation for any alkene stereochemistry, and in fact the EZ system is required once you get past a di-substituted alkene. So if you have a tri-substituted or tetra-substituted alkene, you must use E and Z. Remember, cis and trans is only used when we have two substituents. So remember how the EZ system works. You basically look at each carbon of the double bond, you prioritize the two groups attached according to the Kahn-Ingold-Prelog rules, which are based on atomic number, and then you look to see if the two high priority groups are on Z-same side, giving the Z isomer, or if they're not, it's the E isomer. So here we can see that we have a 1, 2, 3, 4, 5 carbon chain alkene. So this is going to be a pentene. Numbering it would actually start on this left top carbon, placing the alkene on 2. So this is a 2-pentene with a methyl group on 3. And then the stereochemistry would be, in this case, by prioritizing the methyl group on the left over the hydrogen on the left, and the ethyl group on the right over the methyl group on the right. And we can see that the two higher priority groups are not on Z-same side. So this is the E isomer. And we have the same molecule here, but in the complementary stereochemistry, the higher priority groups are on Z-same side. So this is the Z isomer. Next, we have alkynes, which remember are compounds with a carbon-carbon triple bond. And just like with alkenes, alkynes are a suffix modifying group. Here we're changing the ane ending of an alkane to yne to designate that we have an alkyne. So the simplest alkyne would be a 2-carbon alkyne derived from ethane. Here we would change the ane ending to yne, so here we have ethyne. Now, because an alkyne is a suffix modifying group, it actually follows all of the same rules that we apply to the naming of alkenes. The parent chain must be the longest carbon chain that includes the functionalized carbons. And again, with an alkyne, because it has that shared functionality, shared over 2 carbons, we must incorporate both of the alkyne carbons into the parent chain. We would then number the carbons of the parent chain, starting from the end that is closer to the suffix modifying group, closer to the alkyne. So in this case, you can see that we have a 7-carbon chain, alkynes. This is going to be a heptyne. Numbering the carbons from the end that is closer to the triple bond would mean numbering from right to left in this case, actually placing the alkyne on 1. Just like with alkenes, we only place the lower locant value into the name directly in front of the parent name. So here we have 1 heptyne. If we look at the last example, we can see that what we have here is a 9-carbon chain that contains both carbons of the alkyne. So here we're going to have a nonine. And numbering, again, remember that the suffix modifying group has a numbering priority over the prefix modifying group. Here we have an alkyne, but we also have a methyl group. If we numbered our carbon chain starting from the left, that would place the methyl on 2 and the alkyne on 7. If we started numbering the parent chain starting from the right, that would put the alkyne on 2 and the methyl on 8. And because the alkyne is a suffix modifier, it actually has priority. So while it's sort of a 2-to-2 tie for the methyl group versus the alkyne gets priority. So we start numbering from the right, placing the alkyne on 2 and the methyl group on 8. So that means that we have a nonine, a 2-nonine, and then a methyl group on 8. So 8-methyl, 2-nonine. Now, we learned about this idea of degree of substitution, simply counting the number of carbons attached to something, when we looked at alkanes and also at other functional groups. And we saw that for any carbon, you can determine the degree of substitution simply by counting how many other carbons were attached to it. So you could have methyl, primary, secondary, etc. We could then apply that same idea to various functional groups. For things like alcohols and alkyl halides, you would simply count the number of carbons attached to the functionalized carbon. Again, you could have a primary alcohol or a secondary alkyl halide, for example. Alkenes and alkynes, because they are shared functional groups where the double or triple bond is shared between two adjacent carbons, they actually have their own version of this degree of substitution because we have to incorporate how many carbon groups are actually attached to both of the carbons of the pi bond. For alkenes, we're comparing the alkene to the simplest alkene, ethene. If you think of ethene, it's simply a carbon-carbon double bond where all 4 of the groups attached to the carbons are in fact hydrogens. So if you look at this first example, this is considered a monosubstituted alkene, because to make this molecule, we would have to replace one of the hydrogens on ethene with a carbon group, in this case, with an ethyl group. Now, it's called monosubstituted even though it doesn't have any substituents in the name. That's not what we're looking at. We're simply saying how many hydrogens on ethene have been replaced to make this molecule. And in this case, we still have 3 H's directly attached to the carbons of the double bond, so we've replaced one of those hydrogens. It's monosubstituted. If you look at the second example, this is a disubstituted alkene. we've replaced two of the hydrogens on ethene, in this case with methyl groups, in order to form this structure. So this is di-substituted. And then here we have an example of a tri-substituted, here replacing three of the hydrogens, again with methyl groups. And of course, you could also replace all four to create a tetrasubstituted alkene. With alkynes, the degree of substitution is described as either terminal or internal. A terminal alkyne has the triple bond at one of the ends of the carbon chain. So here I have this example of 1-propyne, and you can see that the triple bond is at the very end of the carbon chain. An internal alkyne will have that triple bond somewhere in the middle of the carbon chain, not on the end. So in this example, we have 2-butyne, and you can see that the triple bonded carbons are not on either end of the carbon chain. They're in the middle somewhere. So that is an internal alkyne.